And today, I think we're ready now to welcome our speaker from Australia, Professor Ross McKenzie, who is over here from the University of Queensland for a physics conference here in Cambridge. So we're very happy he's been able to come along and speak to us. He's been in the University of Queensland since 2000, and he's specialising there in condensed matter theory, in mesoscopic electronics, quantum phase transitions, nanomaterials, and other topics that biologists struggle with, rather, but I'm sure we'll be hearing more about those. And these are the topics, really, that have taken Professor McKenzie into particular interest in the whole field of emergence within science, and then in this broader understanding of emergence in the dialogue between science and theology. So he's going to speak to us on that topic today. Thank you, Ross, very much.
Well, thank you. It's wonderful to be here, and particularly exciting just to see all the things that are happening in the Faraday Institute, because I think this dialogue between science and theology is particularly exciting, and I hope that I can just give you a flavour of my perspective on some of this in one particular area, and this is the whole issue of emergence, and particularly the interplay of emergence and reductionism. So let me just give you an overview of what I'm going to talk about. First of all, I'll talk about reductionism in science and try to distinguish between reductionism as a method and reductionism as a philosophy. And then I'm going to talk about emergent phenomena, and I'll particularly talk about some examples which hopefully won't be too technical, but particularly some of them will be motivated by my own field of research, condensed matter physics. But I can begin with a simple example just from geometry that will hopefully illuminate some of the things. And then I'll come to discuss the difference between, if you like, weak and strong emergence, because this is particularly important for when you come to discussing the role of emergence in theology, but before that, I'll talk about reductionism in theology, and particularly emphasise how I think historically reductionism has dominated a lot of theology in the last few centuries. And one of the main points of the talk is that actually the theology of Karl Barth, who was arguably the most influential theologian of the 20th century, has parallels to what you might call an emergent perspective in science. So what is emergence? Well, it's different things to different people. I mean, a very simple definition of what emergence is that the whole is greater than the sum of the parts. But there's more to it. And so these are certain ways you could look at it. If you think of that, you have a system and it's got many constituent parts, and these parts interact with one another. Well, what emergence is about is the fact that when you take the whole system, often it will have properties that are qualitatively different from the properties of the parts of the system. And I'll give some examples soon. Often too, the properties of the whole system are not reducible to the properties of the individual components. And somewhat more controversially, often the properties of the whole cannot be predicted from a knowledge of the properties of the individual components and how they interact with one another. And also often the properties of the whole are not anticipated from a knowledge of the properties of the components. And particularly I'll illustrate from some of my own areas of interest just how clearly this is true. So that's roughly what it is. But like anything, it's easiest to understand in terms of some examples. But on the way to that, one thing we'll appreciate, there's a sort of a stratification of reality and disciplines of study. And so we might start with psychology, which is looking at things on, in a sense, large length scales, large time scales, and very complex things. And we might be able to reduce aspects of that to biology, then down to biochemistry and chemistry and physics. But at each level here, at each strata, if you like, you have phenomena which are distinctly different. I mean, biologists talk about function, and that's a word that doesn't occur in physics. And I'll give later some examples from chemistry. So a very simple way to illustrate emergence and some of the issues, particularly philosophical issues associated with it, in terms of geometry. And this is taken from this nice article, which had the title Chemistry as the Embodiment of Emergence. And so if we think about, we start with just a group of points. We can arrange the points in a certain way to produce a set of line segments. And then if we take two line segments, we can start talking about an angle. But see, an angle has no meaning at all if we're talking about just points. And so the angle is an emergent concept. And then we can go join more lines together and have a surface and so on to a volume. And so this is the idea again. We're increasing the complexity and we've got new phenomena, new concepts involved. And also the kind of concepts and methods we might use at this level will not necessarily be valid or useful at a lower level. So in this article, the author points out three things that geometrical emergence illustrates. So the first one I've mentioned, at any higher level, you have unique properties that are different from those present at the lower strata. Now, another thing is, getting a bit more controversial, is that when you have emergent properties, they can often be rationalized a posteriori, but they're difficult to anticipate. So if we go back here, I mean, if we start with just a surface, or worse, if we just start with, and if we're just living in this, if you like, line world, it's hard, without knowing about the existence of these things, is it easy to anticipate or rationalize those structures? So in a sense, it's when we reduce things, it's really, we're doing things a posteriori. There's something already there, and then we break it down. It's not that we go the other way. And the other thing that's perhaps less controversial is that emergent properties involve taking the properties of the constituents and modifying those. So it brings the constituents into a new relationship. So here, we don't just have four line segments. We have four line segments which are in a particular relationship, which produces the surface. So that's okay. So that's a simple version of emergence. So then I want to talk about emergence in science. And actually, the reason I was in Cambridge was last week. I'm part of something called the International Institute for Complex Adaptive Matter, which is a international materials institute funded by the National Science Foundation, and we have a branch in Queensland, which is funded now by the Australian Research Council. And a lot of we're basically interested in emergent phenomena, originally in condensed matter physics, but now some of us are doing things at the interface of biology, physics and chemistry. And I just mentioned there's some of what we're doing is setting up this website, which is a virtual museum, and it's Emergent Universe. And right now it's a preliminary version of the website, so you have to go to staging if you want to have a look at it. But I really encourage you to look at that and give us any feedback on it. So emergence is at the heart of what I and many other people do. So before talking more about some examples and the philosophical issues, I just want to go back to reductionism. So it's important to distinguish between reductionism as a method and reductionism as a philosophy. And so methodological reductionism would, which again is a at a philosophical level, would claim that the best scientific strategy is always to attempt explanation in terms of ever minute entities. And so micro-reductionism is where you just go down one level. Now this is very, in a sense, non-controversial. You want to understand atoms, and so you look at the individual, you look at the nucleus and individual electrons. You want to understand molecules, you look at the atoms that comprise them. But one of the claims, from a philosophical, is the claim that this is always the best strategy. And that's one thing in this institute, I2Chem, Institute for Complex and Adaptive Matter, and I'll talk about the founder shortly, an emphasis is that this is not always the best strategy. Now, macro-reductionism is something much more bold, and that's really to go down several levels of strata, and so to try and explain social behaviour, for example, in terms of genetics. And so that's a lot of what sociobiologists are like, and a lot of the writing of Richard Dawkins would be based on this. Now, from a philosophical point of view, ontological reductionism is the idea that the only real things are the constituent parts. And so the ultimate reality is what's going on at the lower level. And so it's saying the idea of a human being or a cell is not the fundamental entity or reality. The real reality is the DNA. And so it says we're just DNA. Now, theory reduction, or epistemological reductionism, is the idea that we can always go from one theory down to another, and that they're essentially commensurate with one another. And that's a little less controversial, although people like Thomas Kuhn would say you have certain incommensurations, and so theory reduction isn't always possible. Now, one thing is not to think that I'm anti-reductionist as a method. And the reason why reductionism is so popular as a method, but also as a philosophy, is because it's been very successful. So one that goes back to things at Cambridge and the Cavendish lab is Watson and Crick, who were able to realise that you could understand genetics from the structure of DNA, which was ultimately determined by chemical details like hydrogen bonding. And before that, I mean, a wonderful book, The Nature of the Chemical Bond by Linus Pauling. I mean, Pauling showed that a lot of chemistry you could understand in terms of quantum physics. And then at a lower level in physics, lower strata, Gell-Mann and the theory of quarks. There were all these disparate phenomena in terms of nuclei, baryons, hadrons, different elementary particles, and then a unifying picture which involved symmetry, and quarks was devised by Gell-Mann. And so what micro-reductionism often does is it often brings together many disparate phenomena, because there's all these different phenomena and you can understand them in terms of the constituent parts. And often then these theories are so successful and they get a lot of attention, and rightly so, because they make new predictions, and particularly things that aren't anticipated. So, but the question then is whether this is always the best method, and then also if this, even if it is the best method, which I don't think it is, does that justify any of these different forms of philosophical reductionism? So, in the community I live in condensed matter physics, the whole issue of emergence was highlighted in this article in 1972 in Science by Phil Anderson. Got Nobel Prize in Physics in 1977. If people are familiar with the H-index, his is bigger than 100. In my area, it's just amazing the number of contributions that he's made. But this was just one paper he wrote, which was just on not so much about physics, but how does physics fit into the broader context, and particularly the issue of reductionism and what's fundamental. And one of the points he made is that the success of methodological micro-reductionism doesn't imply a constructivist hypothesis. That is, if we know the laws at some low level, and I'll give an example shortly, we can't necessarily deduce what the laws are at the next level. And so, if we just take physics, and we're talking about an atom and breaking it down to, molecules, breaking down to atoms, nuclei, protons and neutrons and quarks. Knowing the properties of the nuclei and electrons, it's not so easy to necessarily figure out on what's going on up here. And now this is where there are different perspectives. So some people, perhaps like Stephen Weinberg, who are strong reductionists, would say, well, it's just difficult. Basically, they'll acknowledge it's not easy from knowing the laws and forces down here to predict things up here, but we just need adequate computational resources. And so some people would say that, it's just a matter of time. It's just, memory and computer speeds doubling every 18 months, and we might have a quantum computer, and then we'll be able to do this. From knowing the laws down here, we'll figure things out here. Now, what Anderson and later Laughlin and Pines, who I'll introduce shortly, they would tend to say, maybe not in stronger language, well, even if in principle you can do this, this is a bit of a silly exercise because it actually usually produces no real understanding of what's going on, and particularly it can't illuminate what are the fundamental concepts and organising principles involved. But there's other people, and this is where we'll come to strong emergence, who would make much bolder claims that actually that this is logically impossible. I mean, particularly when you go from here up to the biology and so on. But that's a much stronger claim, which I think most physicists would not agree with. So I want to give now a quote from one of my favourite chemists, Roald Hoffmann. I increasingly work at the interface of chemistry and physics, and he writes very beautiful articles and scientific articles, but also popular articles. And he had got the Nobel Prize in 1981, and actually one of the few people who, theoretical chemists, to get a Nobel Prize. And there's this nice book, The Same and Not the Same, and here's a quote from it, which is strong. Okay. Scientists have brought the reductionist mode of thinking as their guiding ideology, yet this philosophy bears so little relationship to the reality within which scientists themselves operate. There are vertical and horizontal ways of understanding. There are concepts in chemistry which are not reducible to physics. Ideas such as aromaticity, acidity and basicity, the concept of a functional group, they cannot be mathematicized, but they are of basic, fantastic utility to our science. And this is from someone who's made their living and fame from using quantum theory to predict properties of molecules and their reactivity. So then I come to the theory of everything. Now this was an article in Proceedings of the National Academy of Sciences published by Bob Laughlin and David Pines. And actually one of the outcomes of this article was the founding of the in the US of the Institute for Complex Adaptive Matter, which has now since become international. I'll say a bit more about Laughlin recently. Is awarded a Nobel Prize and has a nice popular book. But they titled this provocative title for their article, The Theory of Everything. So what's the theory? It's really just two equations. This first equation, some of you may have seen before. This is Schrodinger's equation from quantum physics. But then we need an H here, which is a Hamiltonian, which just tells you the energy in the system. And then for any atom, molecule, crystal, person, one can basically write down more or less what this H is. Okay? It just basically involves kinetic energy and Coulomb's law. So this is not just all of condensed matter physics, which I study, it's all of chemistry, and it's all of biology. This is the theory of everything. If we had, again, the supercomputer, we could, from this, calculate properties of things. So the problem is, well, different people would have different ideas about what the problem is. Well, some people would say, well, the problem is right now, even with the best supercomputer, we can do something with about 8 electrons, or maybe 10, okay? Because, now people might tell you that they do calculations with, thousands of electrons, but often that involves approximations. But to be absolutely sure we're going to get the right answer, we can only do something with about 10 electrons, which is not even a decent sized atom. Well, it's just a matter of time, get a bigger computer. But no, what Laughlin and Pines make the point that there are concepts that you would not even be able to predict. I mean, they give the example of things in superconductivity, even if you had that supercomputer. And another point they make, which I think is important, is that they introduce the idea of protectorates. And the idea here is that higher level laws obscure the content of lower level laws. And then they go further, that the truth of higher level laws can actually be independent of lower level ones. And so a simple example of this is the laws of thermodynamics, which are universal and, as far as we know, true for any material system. But they were actually discovered before people knew about quantum physics. And then later they were found to be consistent with, from something called statistical mechanics, that the laws of thermodynamics you could relate to classical mechanics. But whether or not classical mechanics is right, or quantum mechanics is right, or some new theory we haven't discovered yet, which will be slightly better than quantum mechanics right, doesn't matter. It's irrelevant. The point is, these laws of thermodynamics are, if you like, universal truths that are going to hold, and their truth is not dependent on what's going on at the lower levels. And so some of the point of the article is actually often higher level laws, in a sense you might regard as more fundamental than what goes on at the lower level. So then Laughlin wrote this book. I don't have a date on it. It came out probably about 5 years ago. A Different Universe, Reinventing Physics from the Bottom Down. He's a very colourful personality. He's a very good writer, but I'd certainly recommend it to you. I think it might be pretty heavy going, some of it for non-physicists. But I'll just give you a couple of quotes of things he discusses. One of the things he pursues, which I guess I won't have time to go into detail, which particularly Anderson emphasised in his 1972 article, is there's something called spontaneous symmetry breaking, and that this is a fundamental thing, which is a principle which allows you to understand a lot of what's going on in physics. But Laughlin got the Nobel Prize because he developed the theory of the fractional quantum Hall effect. Now, one of the things that's really strange about this fractional quantum Hall effect is involves where you have these two semiconductors and you look at electrons at the interface between them. And you can measure the currents and voltages and so on. And one of the things that you find is it looks like that the currents are carried by electrons which have fractional charge. And so these are what we call quasi-particles. And so although the system is composed of individual electrons, collectively it looks like it's composed of electrons that have split up into three. And so I'll just say a little bit about quasi-particles, because this is an example in terms of my own research, but also a lot more people, of where strange things happen, and really the sum is greater than the parts. And also when you take the whole system and actually in a sense you want to start dividing it up, you end up with something that's quite different from its constituent parts. And there was a cover story in Nature Physics, I guess it's almost 2 years ago now, and I wrote the News and Views article for this, and that discusses this very issue of quasi-particles in quantum many-body systems. So, yeah, my real living is studying quantum many-body systems. It's where you have many particles, and they're quantum particles, and they interact according to the laws of quantum physics, and what emerges from that? Well, it turns out that in practically every system we know, that it looks like the system behaves like there's weakly interacting collective excitations, which we call quasi-particles. But what's strange is that often these quasi-particles have quantum numbers, which are the basic things that describe them, like their charge and spin and mass, that are different from the constituent particles. So here's a simple way you can probably all relate. If we think about just a single particle, which is then interacting with a lot of particles, or we're thinking about a horse that's running through the desert, but it's running through the it's running through the desert, so it's picking up all this sand, and so the fundamental thing, the thing that you want to understand, is actually not the individual horse and the individual dust particles. It's better just to think of the composite object. And that's the same thing as what goes on in quantum physics, basically, is you have these quasi-particles. And a good way to get a Nobel Prize is to figure out what these quasi-particles are for some particularly interesting system. And that was what Laughlin did. And so this is just one quote of what Laughlin says. He says, "The fractional quantum Hall effect reveals that ostensibly indivisible quanta, in this case the electron with charge E, can be broken into pieces through self-organisation of a phase of matter. And the fundamental things, in other words, are not necessarily fundamental." And so this goes very much against a reductionist perspective. So, if one has an emergent perspective in science, what it seems is that the objects under study are what's going to define how you think about things, what methods you use, what concepts are involved, and in philosophical language, it's basically that ontology determines epistemology. And here's one perspective that I'm going to come back to later, but sciences seek to apprehend a specific object and its environment in a manner directed by the phenomenon itself. And they seek to understand it on its own terms and to speak of it along with all the implications of its existence. So what might we learn in general from an emergent perspective in science? Well, the reductionist emperor has no clothes. It's not all reductionism. And at each level there are irreducible concepts and properties. And at each strata one needs to develop methods, concepts and organising principles that are unique to that strata. And so again, it's ontology determines epistemology. And one thing, these protectorates, if you like, these barriers between strata, between discipline, they affirm the autonomy of disciplines. Chemistry isn't just physics, and biochemistry isn't just chemistry or physics. And another thing is that induction rather than deduction needs to be preeminent in terms of that it's not just a matter of knowing that there's certain axioms and then we deduce from them other things. Doesn't mean that we should be against logic. We should use deduction wherever we can, but often it's really a question of using induction. And again, a posteriori rather than a priori reasoning should be preeminent. It's often that there's something there, there's some phenomena, and we must engage with that. And also then what's fundamental is really a debatable thing, and that's going to be really often something that's going to be a personal judgment. So that's I'd say a perspective on emergence, which would be coming from, well, for me, quoting from a lot of eminent scientists who wouldn't claim reductionism, but a relatively mild form of emergence. And so this is what some people would dub as weak emergence. So before I say what strong emergence is, that weak emergence accepts the limitations, but also the successes of reductionism, and does accept that ultimately emergent properties are determined by fundamental microscopic laws. But, and this is the big but, predicting emergent properties a priori is effectively impossible, and the best scientific strategy to understand emergent phenomena is to develop emergent concepts, principles of self-organisation. And this example of quasi-particles is one of them. And sometimes this would be called epistemological emergence. But particularly in discussions of science theology, there's people who would advocate what might be called strong emergence. And I want to emphasise this is really, particularly from a scientific point of view, is a very radical position. And I mean, this is paraphrased, but emergent properties, they would claim, are not determined by fundamental microscopic laws, but rather by higher level laws. And so biology cannot be understood in terms of physics. And the big controversial one is, they would say that, you're not going to understand consciousness, for example, from neuroscience. And so there's this idea of ontological emergence, that living matter is distinct from inanimate matter. Now, 100 years ago, there were certainly people who strongly, particularly philosophers, advocated this kind of perspective. Another thing that comes down is the idea of top-down causation, and the idea that at higher strata you can have beings and entities there that determine what goes on at the microscopic level. And so most discussions of emergence in theology are within this framework. And I know you had Philip Clayton here give one of the seminars where he would have talked from that. So, maybe. Okay. So, I'm skeptical about this, and I was kind of delighted this way of trying to relate emergence to theology. I found this article. Proctor is a faculty member at University College Santa Barbara, and I think this article is actually a culmination of a Templeton project on resolving multiple visions of nature, science and religion. And he says, emergence has also been offered as a way to situate theology in a scientifically valid framework. And so Philip Clayton's book argues that emergence theory in recent science offers an important opening for language about the spiritual dimension of human existence, including the concept of spirit and perhaps even the idea of God. In its theological extensions, emergence can, if not carefully articulate, become an inspiring but fuzzy God of the gaps argument. So I share some of these concerns, but I think there's a role for emergence. So let me explain it now. So one thing from the history of theology, it appears, particularly after the last few hundred years, is that there has been a lot of reductionism, particularly in liberal theology and particularly in Germany. And so Schleiermacher's perspective was that theology is all about experience. And so to understand God, Christianity, we need to understand the experience of the individual Christian. There are others who the total emphasis was on history and trying to reconstruct the historical Jesus. So people saying that, well, theology is it's about literature. It's about the Bible as literature. And then anthropology, that it's really about religion. And then there's philosophy and even logic. I mean, there's a famous debate between Schultz, who was a theologian who became like a professor of mathematical logic, and considered that theology needed to operate within that framework. But these are people more on the liberal side, but I think it's also true on the more conservative, and very conservative side, and people like Van Til and Carl Henry, who would advocate that in the end theology is a bunch of propositional statements. And that's what, it's about whether these individual statements are true and false. And what theology is about is stating those truths. So again, it's the idea that all of God and theology, knowledge of it, can be reduced to a number of simple statements. So, is there a role for the concept of emergence in the dialogue between science and theology? Well, I think there is, and that's where I found it particularly interesting looking at the theology of Karl Barth. So, those of you who may not be familiar with him, he was trained in German liberal theology, but then became a pastor in Switzerland, and it was actually then, he said, he encountered the strange world of the Bible and the idea of the Word of God and God speaking to people and Jesus himself being the Word of God. And he wrote this commentary on Romans, their Roma brief, and this was it. They say it was like a hand grenade in the academic theological world, and particularly some of his former teachers were incredibly offended. And this was translated into English by Sir Edwin Sykes here at Cambridge, actually. And you can still buy the book; it's in its 6th edition. I really encourage you to even just to dip in and look at a few passages of how he exposits Romans. Barth is also well known because he co-authored, or largely wrote, the Barmen Declaration, which was of pastors who were against Nazi ideology. But he's best known for these 14-volume church dogmatics, which some consider as the most influential theological work since Calvin. And he's definitely the towering figure of 20th century theology, and even if what you read now is people, they might not agree with Barth, but they're trying to distinguish themselves. So what was distinctive about Barth? Well, this was his, I think one of his deriving perspectives. And he gave a series of lectures at Princeton and Chicago towards the end of his life. They're translated into this nice book, Evangelical Theology of Introduction. And one of the things he says is this. He says, sciences seek to apprehend a specific object and its environment in a manner directed by the phenomenon itself. they seek to understand it on its own terms and speak of it along with all the implications of its existence. And so, you notice, that's what I said before, right? I gave you the quote without the source. And for Barth, the object of theology was the triune God. It was God, the Father, Son, and Holy Spirit, the Son being Jesus Christ. And what the Bible was is the record of God's self-revelation. And so, to Barth, there are a number of distinctives, but it's particularly the idea that there is this object and that I've got to understand, and particularly understand it on its own terms. And so, need to start finishing up. So I just highlight a few distinctives of Barth's perspective. And one was that theology is an autonomous discipline. It can and should dialogue with other disciplines, but can't be constrained by them or by their methods or by their concepts. Now, there's a lot of debate about to what extent Barth considered dialogue should go on, and I won't enter into that now, but just there's a range of views on that. But particularly, again, it was this idea that ontology determines epistemology. And theology shouldn't make a priori assumptions about what the nature of revelation is or about the character of God, but it should respond to the revelation that has happened. There is historical events and historical documents, and you have to engage with those. And so he considered theology was nachdenken. It was thinking after the fact. It wasn't where you start with these presuppositions, like I think God is like so-and-so, and well, I see here, Jesus said these things, they're inconsistent with my presuppositions, so it must be that Jesus couldn't have been the Son of God. And he emphasized it was a realism, but a critical realism, but that God is who he is. Yahweh, I am who I am, I'll be what I'll be. And he's who he is, not who we think he is or what he should be. And often there are surprises on the way. And part of that was the idea too, again, that revelation was irreducible. So, let me conclude so we can have some questions. Maybe modest conclusions are that coming from the science point of view, I think we need to acknowledge both the value but also the limitations of reductionism in both science but also in theology. And that there's a lot of science, and I frankly think the most interesting science is about emergent phenomena, and particularly it's at this interface of things like between chemistry and physics, chemistry and biology. And what I think is that but the point to make is that Barth studied the triune God revealed in Jesus Christ, and what's interesting to me is that study drove him to a methodology and a perspective that really resonates with an emergent perspective on science. And that would be one thing that Barth was always emphasizing. It's not that you decide on your method, and so I'm not advocating at all because emergent perspective is good in science, it must be good in theology. All I'm saying, it's interesting that that Barth had a particular object in mind, and that led him to a particular perspective. So I'll stop there and welcome questions.
Thank you very much, Ross. I'm sure that stimulated plenty of questions, so over to you for... Yes, a question.
Yeah. Thank you very much indeed. I wonder whether you might be able to say anything about the role of emergence in cosmology. I'm thinking about, as much as I understand it, the work of people like Paul Davies, where they talk about maybe consciousness, matter, and law somehow merging together in the universe throughout the. How does that idea relate to what you said there?
Well, just that, and I think Paul Davies might push some of the on the science side, some of these ideas a lot harder. I mean, my perspective would just be that again, there's emergence in a lot of science, and so historically, I mean, in terms of the history of the universe, things do emerge, and so you started with galaxies, which then emerged to something else, and then from the planets, eventually, life emerges. But I mean, and there are books that try to. Harold Morowitz has this book where he tries to go the full continuum of things emerging from atoms and quarks to sort of consciousness and society. So I'm not sure that's...
Where it gets a bit, so just a quick follow-up, it's the comments that sometimes you read things like the universe saw us coming and stuff like that. That's kind of what I was hoping to push you.
Right, that's particularly right to the and that really relates to the anthropic principle. I think particularly they say that because of there's all these coincidences. So maybe we should talk more later. I can't give you a sort of succinct, coherent answer.
Okay. Yes, question. Yeah. Yes.
I'd like to ask about methods and methodology. If one is a classic scientist in reductionist mode, one can think what your method would be in order to pursue that. But how does that change, particularly if you become a strong emergence person? What kind of scientific method would you follow practically?
Well, I think the strong emergence, I think that's more, I think it's problematic for science, for traditional science, and I think it's largely a philosophical point of view.
That's why I said particularly strong.
Yeah, I think the whole thing is problematic, frankly, but I'd love to discuss it. But the weak emergence, that's what a lot of what me and some of my colleagues are about, is that for emergent phenomena, which is most of, like what I do, condensed metaphysics, most of the interesting stuff, the best strategy is you look for what are the organisational principles. So for what's going on. Maybe I'll give an example that would make it more accessible to everyone. So the question is, if you want to understand social behaviour, the first step isn't to start to thinking about individual psychology and how individual people interact with one another. And that rather, I think a better strategy is you think about what organisational principles do you see at work in social behaviour, and then if you figured out what those principles are, maybe you might be able to then break them down and relate them to individual, what happens at individual levels and what those interactions are. And that's where then the both strata value is that the social psychologist can have a constructive interaction with the person who studies individual persons, and they can try and make some connection. I mean, and then in terms of what I do in my everyday life, we look at some phenomena like superconductivity, which occurs in lots of different materials, and we understand that on its own terms, but then we, at various levels, we can then relate that to what's going on lower down. So some of it's in terms of methodology, but also some of it is in terms of just perspective. And I think ultimately too in terms of value, that the disciplines and things are autonomous, and it's not that one is more fundamental than another.
Can I just press you a little bit, Ross, on that? So what you're saying is in your particular field, to adopt that particular emergentist research program is going to be, in your view, a more fruitful research program. It's going to lead to better insights, better publications, better... That's important.
And I'll go out on a limb here, and we're all recorded. So in terms of what I do, if there's a new materials we want to understand. Now, what too many people do now with the advent of computational resources and these user-friendly quantum chemistry packages, they try to start with what's the original crystal structure and compositions of the atoms and molecules, how they are in relation, and then predict things at the highest level. And increasingly, there are resources and energy going into that, and less into where people look more at what the phenomena is, whether it's superconductivity or magnetism, and then how one can look at that in terms of a model which doesn't worry about basically the chemical the chemical details. So, and I think, yeah, I'll say that. And I think if you look at the history, that this is where the real point, and that was some of Phil Anderson's point. Yeah.
Right. Yes.
Isn't the word you just mentioned for the first time a critical one here, and that is model?
Yeah.
In other words, you're dealing with whatever phenomena you're studying with a certain kind of model in mind. And so that the models that you use for one purpose are not necessarily applicable for another. And what's more important, the limitations of models that you use at one level will spill into the higher level if you're not aware of what they are. And one sees that in all sorts of modelling, which could go from the models that the Treasury operates and comes up with answers that nobody can believe anymore, if they ever did. And the example you were giving of people trying to predict higher level phenomena with the mathematical basis of some relatively simple methods.
Yeah, no, I think that's a good way to look at it. Yep.
Right, there's a question back here. No? Okay. Other questions? Yes. Bob, and then yes, and then James.
Can I go right back to the asymmetry you mentioned right at the beginning, where you said it bothers you that you can't predict some higher order phenomenon, versus the asymmetry of looking back and being able to understand it. And I wonder why that bothers you, because just to take a little example, you're walking through a forest, there's a juncture with 6 different ways, you take that way, you get chased by a bear. When you're sitting down in the evening because you ran fast enough to get away from it, you think, I was chased by that bear because I made that decision at that junction. It's all very explicable. But before you came to the junction, you don't know what's ahead of you. So why does it bother you that you can't predict higher order phenomena from lower order levels when you can work the other way?
Well, I think that's the thing. I think it doesn't bother me, and I'm perfectly comfortable with that. But I think there's people who think both that particularly I think there's a lot of people who think they can predict, because they can go down. And this was Anderson's point. People think because they can go down, they can therefore go up, and therefore that when they understand what happens at the lower level, they actually understand what goes on at the higher level. So I think, yeah.
I mean, mine was the classic reductionist viewpoint, which works pragmatically. You can look back and see why things have happened.
Well, it's not quite. I think if you read, for example, Stephen Weinberg. So I guess would you say that Stephen Weinberg and Richard Dawkins are classic reductionists? But maybe we should.
James, question.
I was wondering if you could comment on the appropriateness of using the language of causation to go between different strata. So people in Emergence, talking about Emergence, often talk about top-down and bottom-up causation.
Right.
I'm wondering if that is appropriate, and I want to think about a very simple model, which is lines going to angles. If you have 2 lines which form an angle, do those lines cause that angle, or is the angle just the kind of confluence of those 2 lines?
Yeah, I think, and that's some of what I think is beautiful and important about appreciating these strata, is it does raise questions about causality. And so I'll give you 2 quotes. One is from Bob Laughlin, who says something along the lines of, we know that different phases of matter, solid, liquid and gas, are caused by interactions between atoms and molecules. But he claims that it's in terms of understanding the spontaneous symmetry breaking and stuff, which helps you understand those phases, and that's as much as causality. And he says, it's just like, well, what caused Tokyo to be destroyed? You could say it was chemistry, but actually the real explanation, the better explanation, is Godzilla destroyed Tokyo. And so, again, I think the language of causality gets confused, and that when you're thinking from a emergent perspective, I think it clarifies some of that, and it goes against the idea that of this classic reductionist point of view that everything's caused, how I relate to my life. Life is caused by, biochemistry, by Schrödinger's equation. The other quote then comes from the other extreme, relates to Karl Barth. When the Church Dogmatics, he wrote many volumes over many years, but the English translation of the first volume was done by Thomas Torrance and Geoffrey Bromley, and in the preface to that, they say that of the first volume of Church Dogmatics, that basically what Barth has done is shown that theology cannot be reduced to anthropology. And that was, and particularly in the historical context, that was a major achievement.
Question at the back there, yes.
I wanted to press you on the distinction you made between a weak and a strong emergence. Because if you adopt the weak emergent perspective, what are your ontological commitments to the application of concepts which you don't need the theory at the bottom strata at the level of quarks? Because if you are going to claim that there are actually real things, which could, for instance, be causally efficacious, which are not at the lowest level of description, you do seem to be making an ontological commitment of the kind which you characterised as strong emergentism. And if you don't, then how much emergentism have you left?
Okay, it's a great question, and I don't think I have a clear answer. That, and I think that some of my thinking is muddy on this, and needs to clarify. But it gets down to this question of of ontology in terms of what are the real things, and I guess my perspective right now would be that although the quasi-particle is a collective object involving many electrons, to me the quasi-particle is just as real and an entity as the individual electrons, and that we shouldn't put higher priority on one or the other. Now, I would say that's I wouldn't say committing to myself to that as going as strong emergence. Would you agree that that's, by saying that, I'm not going to strong emergence? Or?
Well, are you sort of taking it that it is the choice that you're making, which you take at any given time to be basically the quasi-particle or particle?
Yeah.
So it's a kind of anti-realism about which is most fundamental.
Oh, I never call myself an anti-real. Maybe we should talk. I mean, I would like to talk more about this, because there are, again, I'm not a philosopher of science, and I read some of this stuff and grapple trying to figure out where I fit in the spectrum.
I think we are actually going to have to draw to a close. It's 2 o'clock, and I should just mention, before thanking Ross again, that there's going to be another meeting here, which means we have to leave by 2:15. That gives a little bit of time for follow-up discussions with Ross, or going off to the pub afterwards if he's got time, or whatever, I don't know, tea. But, I think first of all we really want to thank Ross McKenzie for a very stimulating talk. So.